In this set of notes, we're going to look at what is known as integration by parts. Previously, we saw that when taking the derivative of a product of functions, we needed to apply the product rule. So it would stand to reason if we need to find a way to reverse the product rule or to work backwards. Integration by parts is the integration equivalent to the product rule in differentiation. And so here's what the rule looks like. So if u of x and v of x are differentiable functions, then if we take the integral of u of v times the derivative of v, u of x times the derivative of v, this is equal to the product of the functions minus the integral of the derivative of u times the derivative of v. And so at first, you might say, well, how does this really help me? If we look at the original integral, we have u times the derivative of v, whereas here we have the derivative of u times v. Well, it ends up that what happens is this one is usually much easier to work with than this one. And your book takes a look at how we could derive this based off of what we know about the product rule. And so I highly, recommend, as always, reading through the chapter of your book and looking at that particular spot. Now we are going to look at some examples of how we can apply this rule. All right, so we want to evaluate the indefinite integral that we have here. So the very first thing to notice is that we do have a product of two different functions. So here we have 3x times e to the negative 2x. So since we have two different functions of x and we're multiplying them together, we know that if we were to want to take the derivative of the product of these functions, we would use the product rule. But here we want to integrate the product of these two functions. And so we're actually going to apply, again, this integration by parts, because you can kind of think of that as the opposite of the product rule. All right. Now, in order to do this, what we need to do is we need to designate one of these functions to be u and one of them to be equal to the derivative of v. And we want to choose u and the derivative of v so that when we look at the product of u prime times v, that is simpler than u times v prime. And so in other words, however we define this, in the original integral, we're going to have a u times v prime, but remember, and we can see this up here in this box, when we actually find the integral, that's going to become u prime times v. And so in this case, notice that the function e to the negative 2x, that's not going to get any simpler. And we know that because whenever we take the derivative of e to any power, it's still going to involve e to any power, and the same thing if we were to integrate. So let's try u equal to 3x and v prime equal to e to the negative 2x. Now this suggests that u prime is equal to 3 and v, so notice here we've got the derivative and we're looking for the function that is the derivative of. In other words, we're really thinking of integration here. Notice this is equal to 1/2 e to the negative 2x. So let's use that information in the box up above and write out what our new integral is going to look like. So we started out with the integral of 3x e to the negative 2x dx. And we defined u to be 3x and v prime to be equal to 2 to the negative 2x. Well, again, going back up to our rule, notice the first thing that we're going to have is u times v. So u in this case is 3x times v, which is negative 1/2 e to the negative 2x. Next, we're going to subtract off the integral of u prime times v. Well, u prime in this case is just 3, and again v is negative 1/2 e to the negative 2x dx. So this becomes 3 divided by 2, and that's going to be a negative x e to the negative 2x, so I just simplified that, minus, I'm going to go ahead and pull out my constants here. So that's going to be 3 times negative 1/2, so this is going to become a positive 3/2 times the integral of e to the negative 2x dx. And now we have an integral that we know how to work with. We've worked with integrals like that in the past. So just rewriting that first term. And now we're going to have 3/2 times negative 1/2 e to the negative 2x plus c. And then just multiplying those constants. We have the following. And so again, notice on this example, once we applied the integration by parts, we still had an integral that we had to deal with, but working with this integral is much easier than working with this integral. And so that's what integration by parts does, is it helps you simplify it so you get an easier integral to work with. Now, identifying which function should be the u and which one should be the v prime is not always the easiest thing to do. And so I think students get really intimidated sometimes by this very first step of, well, how do we choose u and how do we choose v prime? And in all honesty, in practice, sometimes it's just trial and error. So if you try a u and a v prime and you get down here and you realize that new integral you're working with isn't simpler, then try a different u and v prime. And so it will take some trial and error. You won't always get u and v prime right off the bat. Now I will say, typically if you're working with like e to the power of something, that is usually going to be the v, or be the v prime. But again, it's going to depend on what you're working with, so don't be afraid of some trial and error here. Typically when I work with integrals like this, I'm almost always working on scratch paper first, because I realize it might take me a couple tries to realize how exactly I want to apply the integration by parts. All right, let's look at another example here. So here we have the integral of x squared natural log of x squared dx. And so again, notice we have two different functions. Our first function is x squared, and the second one is the natural log of x squared, and we have the product of these two functions. So the very first thing that we need to do is we need to identify what our u and our v prime are. And so again, it might take you some trial and error. Now in this case, I know that, u prime is going to end up in the integral piece, that new integral piece that I'm going to have. And so keeping this in mind, I know that if I take the derivative of the natural log of x squared, well, that derivative is going to be, we're going to have to apply the chain rule, but the derivative of log of x is 1 over x, and so that might be a simpler one to work with if I have to integrate with u prime. So for that reason, let's start out with u equal to the natural log of x squared and v prime equal to x squared. So then that's going to suggest, again, this is by the chain rule here, that the derivative of u is going to be equal to 1 over x squared. And then, of course, because of the chain rule, we need to multiply by the derivative of x squared, which is 2x. So this is equal to 2x over x squared. And notice that just leaves us with 2 over x. And v, well, here, again, we've got the derivative. We're looking for the function. We're essentially integrating x squared. So we're applying kind of that reverse power rule that we've talked about several times. That's going to be equal to 1/3 x cubed. So now we can set up our integration. So we have the integral of x squared natural log of x squared dx. And then applying our integration by parts, this is going to be equal to u times v. So we're going to have the natural log of x squared times 1/3 x cubed minus the integral of u prime times v. So this is going to be 2 over x times 1/3 x cubed dx. So rewriting this, I'm just going to rearrange this first term. I've got 1/3 x cubed times the natural log of x squared minus, I'm going to go ahead and pull out my constant, so I've got minus 2/3. And notice here we've got x cubed divided by x, so this is just going to be the integral of x squared dx. So our first term isn't changing. And integrating x squared, much easier than integrating that first term that we had. Again, this is just going to be applying that reversed power rule. And so this is going to become x to the third times 1/3 plus c. And so we end up with the following. So again, these are a little bit tedious, but if we make a good choice of u and v prime, we do end up with a much easier integral to work with. And again, that is the benefit of using integration by parts. Okay, so we've got one more example here. And so notice here again, we have a function, but this time it's not clear how we have a product of functions. So here we've got the natural log of x plus 1, but there are cases where it helps if we actually think of one of our functions as just being the constant function 1. And this is actually an example of a case like this, and your book looks at an example like this where you just have the natural log of x. So again, we're going to look here at the natural log of x plus 1. So we're going to let f of x equal to 1 be one of the functions in the product. Okay. So here we're going to have u is equal to the natural log of x plus 1. And again, we're going to put the log function with the u for the same reason that we did in the previous example. That's because we know the derivative of the log is going to be equal to 1 over whatever's on, the function on the inside. And then, of course, we have to apply the chain rule. But that means that u prime is going to be much simpler to work with than u. And so that would mean that v prime is equal to 1. All right, so now taking the derivative of u, notice that's going to be 1 over x squared, 1 over x plus 1, I'm tongue-tied here. And then, of course, we're applying the chain rule, but notice that the derivative of the inner function here is x plus 1 is just equal to 1. And then if we integrate 1, of course, that's just going to be equal to x. All right, so working with our integral, here we have a definite integral from 1 to 2. And we have the natural log of x plus 1 dx. Well, the first thing that we're going to do is multiply the u and the v together. So notice I'm going to have x times the natural log of x plus 1. Now, here is one of the differences between the definite and the indefinite integral. Remember, for the definite integral, we're evaluating over the interval from 1 to 2. So this first piece of the integral, we also need to evaluate it from 1 to 2. And so I'm going to evaluate this piece from 1 to 2. And then I'm going to subtract off that integral piece. And so this will again be the integral from 1 to 2. But notice it's going to be the integral from 1 to 2 of u prime times v, which is x over x plus 1. And it ends up that this function is going to be much easier to work with. So we'll keep the first term just for right now. Actually, we can go ahead and evaluate it from 1 to 2. So notice if we plug in 2, we're going to get 2 times the natural log of 3. And then, of course, we need to minus this evaluated at 1. So that would be 1 times the natural log of 2. So that takes care of that first term. And then again, we need to subtract off the integral piece, so let's go ahead and evaluate that integral. Now, at first looking at this, we've got x over x plus 1. This might be a little bit difficult to integrate, but one thing that we could do, and this is a very common trick that is used when you have a fraction that looks like this. Notice that this is equal to the integral. Now, in the numerator, what I'm going to do is I'm just going to add 1 and subtract 1. And at first you might say, well, why do we want to do that? Well, the reason for that is notice I can now write this as the following. So my first two terms are just going to stay the same. But we could keep that x plus 1 together as one term and then the minus 1 on its own. So this becomes x plus 1 divided by x plus 1 minus 1 over x plus 1 dx. This first term here is just the number 1. So now I just have 1 minus 1 over x plus 1 dx. And again, the whole idea is I'm just keep on manipulating things to make it till I get to an integral that is really easy to work with. So this is equal to 2 times the natural log of 3 minus the natural log of 2 minus the integral from 1 to 2, 1 dx minus the definite integral from 1 to 2 of 1 over x plus 1 dx. And now finally, this is going to be equal to 2 times the natural log of 3 minus the natural log of 2. Now we know that the integral from 1 to 2, 1 dx, well, that's just going to be equal to the function x evaluated from 1 to 2. And then our second derivative, or our second integral that we have here, well, we've got 1 over x plus 1. So that is the same thing as the natural log of the absolute value of x plus 1 once we take that integration. And so that's coming back from the previous chapter. That's one of those more simple integrations that we can work with. And again, we're going to evaluate this absolute value from 1 to 2. So now, doing the evaluation, we've got 2 natural log of 3 minus the natural log of 2. We're going to subtract off x evaluated from 2 to 1. Well, that's the same thing as minus 2 minus 1. And then we're going to subtract off this log evaluated at 2. So that's just the natural log of 3 minus the natural log of 2. And so combining all of our terms here, nope, I think I have missed a minus sign here. Double check that real quick. Yep, so notice here we've got minus the integral, and so this one's positive and then negative, minus the integral, the positive, negative. So when I split up the integrals, this one actually becomes positive, so let me change that really quick throughout here. Alright, so now we can go through and combine our like terms. So notice I've got 2 times the natural log of 3, and then I've got a natural log of 3 down here. So I'm going to have 3 times the natural log of 3. For the natural log of 2, I've got minus the natural log of 2, and a second minus the natural log of 2, so that's minus 2 natural log of 2. And then finally, I've got minus 2 plus 1, and we have minus 1. And so that is our final answer. And so again, the real benefit to integration by parts is that we end up with an integral that's easier to work with. So we're not completely eliminating the integral, it's just we're trying to manipulate things until we get down to an integral that is much, much easier to work with. And again, I do want to iterate, one of the hardest parts of integration is trying to figure out which rules to use and then how to best to apply those rules. And in all honesty, that just takes trial and error and lots of practice. So the rest of this section of the textbook talks about that topic. It gives you some different hints and tricks for trying to identify which rule is the best, and then also just lots of practice with integration. So I highly recommend, reading all of the examples in the textbook. I've used different examples here in the notes because, again, the more examples that you expose yourself to, the more examples that you try, the easier these are going to become. So as always, if you have any questions, please let me know.